Hello everyone, welcome back all of you in my YouTube channel. In this video I am going to talk about the very basic concept of general theory of relativity, the Michelson-Morley experiment. So before beginning this experiment in mathematical interpretation, we should know why this experiment has been performed. So in the late 19th century, it was very famously regarded as there is a hypothetical medium pervade in the universe everywhere named as ether. So to identify the basic presence of that particular kind of medium known as ether, this experiment has been performed by Michelson and Morley in the late 19th century, approximately in 1880 or 1881. So this was the basic reason behind the performance of this experiment. After the revolution, the relativity revolution done by the Einstein, this was has been regarded as the particular kind of medium ether. And after the introduction of spatial theory of relativity given by the Einstein, these all the kinds of medium has been ruled out. So what exactly this experiment was? Let us look at the experimental setup first of all of this kind of experiment. So on the board you can see here I have shown the two mirrors, mirror M1 and mirror M2. Both mirrors are taken as perpendicular to each other. If I put this mirror M1 here, then that will be regarded as a perpendicular to mirror M2. We have also taken as partially silvered mirror, which was taken in the Michelson-Morley experiment. This partially silvered mirror was done so that whenever a light ray comes at such kind of source, that will fall over this partially silvered mirror, and this mirror will allow that particular light to reflect and to refract as well. That's why this has been taken as partially silvered. Also you can see here interferometer or telescope I have made. In the Michelson-Morley experiment, the telescope has been taken to see what exactly is happening at this point P or in the partially silvered mirror. And this is the light source, monochromatic light source. Okay. So what was the mathematical interpretation of this experiment? So let us discuss about that. You can see here from this monochromatic light source S, a light ray coloring as green coming from this light source S and is making fall on this point P. As this is partially silvered mirror, this will allow a part of this coming ray to reflect as well as refract. So that part that is refract from this partially silvered mirror falls over the mirror M1 and turns back after the reflection with this mirror, and again it comes at point P. Okay, this is done. Now the part that has been reflected towards the M2, that again turns back after the reflection at the point M2 and comes at point P. Now these two kinds of rays which are coming from the point F1 after the reflection, and the another part of ray which is coming from this point M2 after this reflection interferes at this point P, and the interference happening can easily be seen that by the interferometer or telescope with our eye. So what will be happen at this point P, that will actually seen by the interferometer. So that's why we have taken the telescope here. Okay. So to identify the presence of ether or to calculate the relative velocity of medium ether with respect to Earth, or the relative velocity of Earth with respect to medium, we can suppose as the Earth can be taken as one kind of frame of reference. So I have made here Earth is taken as S dash frame of reference, which is moving with velocity b in the frame of reference ether S. So ether is shown here as frame of reference S, in which Earth, which is regarded as S dash frame of reference moving with velocity b. So by calculating the relative velocity of the Earth v with respect to the medium S, we can sure that there is a medium like the ether. Actually, there is no medium such kind of ether. This was ruled out in the late 19th century. Pervaded as 1880, or that was done by the scientist Einstein. Okay, so in this video we are going to discuss what exactly was the experimental setup and what was the negative or positive results of the Michelson-Morley experiment. Okay, so I'm going to start the mathematical interpretation of this experimental setup. Okay, so first of all, I will calculate the total time taken by the ray in this path and after its reflection in this path. So the time taken by the ray going towards M1, let's say this is T1, T1A. Okay, so time T1A will be equals to the distance and divided by the velocity. So the distance, let's say from point P1 to mirror M1, or the mirror M1 is situated from this complete mirror as distance as L. So this is the L divided by the velocity of the light by which it is going towards the mirror M1. So the velocity can be calculated by using the Gaussian transformation. Gaussian transformation are Vx dash equals Vx minus V. Let me make you understand here what are the exactly meaning by Vx dash, Vx and V here. As light is going towards the x-axis positive direction, Vx dash is showing the component of the speed of light in the frame of reference of Earth as dash, because dash is taken here. So Vx dash or Vx prime is the component of speed of light in S dash frame of reference or in Earth, and Vx is nothing but the velocity of the speed of the light in ether frame, and V is the speed of Earth in the ether. Okay, so this is what we have the Gaussian transformation for the speed of light. So Vx is nothing but the speed of light in the ether, and as ether is pervaded in the universe in the stationary conditions, so the light will move in the ether with its absolute value. And what is the value of the speed in the stationary kind of system? That is c. So I will take here as c, and this is minus v. So this is what we have, Vx dash, the component of the speed of light in the S dash frame, because this experimental setup is situated on the Earth. So we will take the Vx prime component of the speed of light. Okay, now I can put here Vx dash in the denominator of L. So this is c minus v. C minus v is the time taken by the ray from going from point here to there. Okay, again I can also write here as time t1b. Time t1b is showing the time taken by the ray coming from point M1 to again P. Okay, in this condition the velocity component again from the Gaussian transformation can be written as Vx. Vx is nothing but the speed of light in the ether. Now light ray is coming in the x negative direction, so I will take it as minus c here, and this is minus v. Okay, minus can be taken as common. This is again c plus v, Vx dash. As this is the velocity minus c plus v, I can put this velocity value in the equation. This is L over the velocity. Here I will take out as here the magnitude of the velocity, not the negative sign, because time cannot be negative. Okay, so this will be only c plus v. I have neglected the negative sign. So you can also see here the length travels y, the light from reaching point P to M1 will be same as that from M1 to P, because this length is L, so this length will be as L. So I have taken the same length here and here also. Now the total time taken by the ray at reaching point M1 and reflecting back at point P will be T1 equals T1A plus time T1B. So let me add these two equations. Here L is common, and the rest terms are 1 upon c minus v plus 1 upon c plus v. You can solve this equation by the simple algebra law. These are the c minus v and c plus v, and c plus v plus c minus v. V is cancelled by v, and the rest terms are 2c times of L. This is 2cl divided by c square minus v square. Okay, for the convenient to make this equation as good situation, I can take c square as common in the denominator. So that will be 2cl over c square, and here 1 minus v square upon c square will be rest. C is cancelled by C, so rest is 12 upon C times of 1 minus B square upon C square. Okay, this is the time T1 what we have up till now. So T1 is the time taken by the ray. Total time taken by the ray from at reaching at point M1 and reflecting back at point M2 here. Okay, in the same way I can also calculate the time taken by this ray in reaching at point M2 and then coming back at point P. Okay, so I am doing the same. So in order to do that, I will have need the velocity, okay, velocity of the light in the y-axis. Okay, again I am using the Galilean transformation, Vx dash equals Vx minus V. Now you can easily see here there is no component of speed of light in the y-axis, okay, because light is going towards the x-axis, so there will no component in the y-axis here. So this component will be 0 and this will be Vx minus V or Vx equals to V. What about the y component according to Galilean transformation? That will be Vy dash equals to Vy. There is no change in the y-axis according to Galilean transformation. Okay, so from these two equations I can find the Vy prime. In order to do that, I am squaring and adding equation 1 and 2 with each other. So Vx square plus Vy square I will get from here, Vx square plus Vy square, and that will be B square plus Vy square prime. Okay, so up till now we have this value. Now you can easily see here that Vx square plus Vy square, if it would be Bz square, then that will be the magnitude of the velocity of light in the space. So here z-axis is not taken, that's why Vx square plus Vy square simultaneously will be taken as c square. So this is the c square equals to V square plus By prime square. So from the equation I can easily find the By prime. So this is By prime equals square root of c square minus V square. Right, so this is the velocity component of speed of light in the y-axis. Okay, now I can easily find the time taken by the ray towards the y-axis. Okay, so let's say the time taken by the ray towards the y-axis for this arrow, this is time t2a and this is the time t2b. Okay, so in the positive y-axis I will take the time t2a here, that will be equals to L over the velocity. I have told you both the mirrors are situated at the same distance from this partially silvered mirror. This is the L, this is as well as L. Okay, so distance over velocity. Velocity is nothing but c square minus v square. Okay, again you can see here Earth is not moving in the y-axis, so the Earth component in the y-axis has been 0, just as I have written it as here. So the time taken by the ray to go from point P to M2 will be same as that of the time taken by the ray from reflecting back from point M2 to point P. So these two times will be same. So T2B will also be L over under root c square minus b square. Total time will be T2 equals T2A plus time T2B. This is the total time for this by-axis ray. They will be these two equation addition, that will be 12 over under root c square minus b square. For the convenient, again I can take c square as common from this square root, that will come out as c, and that will 1 minus b square over c square here. Okay, so these are the times what we have up till now. Okay, now let me remove these extra terms here. Now you can see here I have the time t1 and t2. Let me tell you again, t1 is the time taken by the ray to come at point M1 and reflecting back at point P from the M1, as well as the time T2 is the taken by the ray from this Y consideration. Okay. What is the time difference between these two rays? Let us talk about that. So time difference between these two rays will be, let's say this is the simple T or delta T. Delta T will be this minus that or that minus this. Which one quantity is greater? So that is this one minus that one. So this one will be 12 over C and 1 minus B square over C square minus 12 over C and under root 1 minus B square over C square. This is the time difference between these two rays, which one is taken on the x-axis and another is taken on the y-axis. Let me solve these two equations. 2L is common here. Also C is common here. This is 1 upon 1 minus B square upon C square minus 1 upon under root 1 minus V square upon C square. I can use here as the binomial expansion. This is 1 over. This is 1 minus B square upon C square whole raised to power minus 1. I have taken this denominator into the numerator complete as minus. This can also be taken in the numerator 1 minus B square upon C square whole raised to power minus 1 by 2. Okay, because under root means 1 by 2 and in the numerator that will become as negative. So this is 12 upon C, and by the binomial theorem this negative power will be in the multiply and that minus minus plus for the lowest terms, for the initial terms of this binomial expansion, and minus this will also written as 1 plus this minus 1 by 2 will be in the multiply of the B square over C square, that will become 1 over 2 times of B square over C square. Okay, again this is 12 over C 1 plus B square over C square minus 1 by 2 V square upon C square. This one is cancelled by this one. This is 12 over C and B square upon C square minus V square upon 2 C square. This is the half of the B square over C square. So remaining term will be B square over 2 C square. Again you can see here 2 is cancelled by 2 and this becomes L over L B square upon C cube. Okay, so this is what we have up till now, the time difference between these two rays. Okay, why we have calculating the time difference? Whatever the time difference between these two rays, that should be same as that of the time difference between these two rays when we will move this complete experimental setup as 90 degree. Okay, let me do that. This is V square L upon C cube here. So the time difference is delta T is V square L over C cube here. Okay. Now what we are going to do, Michelson Morley done so. Now this complete setup has been rotated up to 90 degree in any direction, clockwise or anti-clockwise. What will happen? This mirror M1 will take place of mirror M2 and mirror M2 will go at here. Okay, in that particular condition, this complete time, this was T1 and this is a complete time T2, will be reversed, will be replaced to each other. Now T1 will become T2 and T2 will become T1, right? So in that particular condition, when we will find the time difference between these two particular kinds of rays, then that will be what? That will be the double. Okay, let me write it as here. Now T2 will be T1 and its vice versa also too. T1 will be T2. So whatever be the time difference between these two rays we are finding up till now here, that will be same. The time difference between the rays when this mirror M1 will take place M2 and M2 will be at here. So the time difference between these two conditions will be same. So the complete total time in these two particular conditions will be what? Twice of this particular quantity. Let me write it as here. Now I have shown this mirror M1 as here and this M2 as here. Okay, and the interferometer will be at this point, and the light source will be at here. Now this time will be T1, this time will be T2. Now you can actually see here as now T1 what was at here, that will become T2 along the x-axis, and what was the T2, now it becomes as T1. Okay, now again we will find the time difference between these two rays, that will be going as equal, because there is no change as a simple experimental setup changes. Okay, so that particular time will be same as that this quantity. So the complete time will be as 2b square L upon CQ. This is a total time. Now this particular total time difference, there will be a shift in the fringes. Okay, in the first case, when this complete ray has been coming at this point P and this ray coming from mirror M2 at point P, they interferes at point P and makes interference fringes. Okay, the interference fringes that will obtain at here as these strips can be easily seen by this telescope. Okay, but when we have rotated this complete experimental setup up to 90 degree, okay, there should be a fringe difference. Okay, because now T1 becomes T2 and T2 becomes T1. So whatever be the change in the or shift in the fringes, that can be calculated. How? This is a time difference or total time between these two particular rays in two conditions. Now if I am interested to find the particular fringe shifting, then I should have the, let me write it as here. I have time difference. In order to find the fringe width or fringe pattern, I should have the path difference, because whatever be the fringe shift, that will equal to the path difference of these two rays coming from point M1 to P and M2 to P, and in particular condition when we have rotated this as up to 90 degree. Okay, so that will be, let's say the time path difference delta x is nothing but the delta t times of velocity of light is just c. So I have calculated it as time difference, this is 2b square L upon c cube multiplied by c, and this c is cancelled by c cube by 2 powers. This is 2b square L upon c. This is particular we have up to now the path difference, and that path difference should be equals to the fringe shift. Okay, so let me put this complete path difference equals to the fringe shift. This is 2b square L upon c only, c square, so this is c square here, and that will be equals to path fringe shift. Let's say n fringes are shifted having the wavelength lambda, so the path difference, this one, will be equal to the fringe shift. Okay, now you can check here as n, this is what we have up till 2v square L upon c square and lambda. Now I can put at here the actual value taken by the Michelson and Morley in his experiment. Okay, so this will be 2. V is the velocity of Earth in the frame of reference ether. It can be taken as the orbital velocity of the Earth, and that is nothing but 3 times 10 to the power 4 meter per second, and it's a square is taken. L in the Michelson Morley experiment was taken as approximately 11 to 12 meter. Okay, and divided by c square, 3 times 10 to the power 8 whole square times of lambda, and this monochromatic light source was taken as 5500 angstrom or 5.5 times 10 to the power minus 7. When you solve this complete factor, you will get, let me solve this complete factor here. 5.5 times 10 to the power minus 7. This will come out as 0.456, 0.4 approximately. So this will be the fringe shift. This much fringe shift will occur if B will perform such kind of experimental setup and such kind of consideration. But actually what has been concluded or what has been achieved by this experimental setup? Actually, when this experimental setup has been designed or this complete experiment was performed by the Michelson and Morley, no fringe shift has been obtained. Okay, so this complete experimental setup had given no results. That's why this complete experiment or experimental setup has been ruled out. Okay, so mathematically we have performed 0.4 fringe shift when we tilt this complete experimental setup up to 90 degree, but in actual we didn't get any kind of fringe shift. In the many times we have Michelson Morley performed this kind of experiment to see the fringe shift, but at the same time, at the many times they didn't get any kind of fringe shift. They performed this complete experimental setup or this complete experiment at the different kinds of weather and different kinds of months or years even. They did not get any kind of fringe shift. And the conclusion was that the presence of ether has been ruled out. And what exactly were the postulates which has been come from this complete experiment? Einstein has given his postulates on the basis of this Michelson-Morley experiment. So up till now we had whatever we have discussed, this has given no results, because if we compare the mathematical interpretations with the actual value what the Michelson-Morley has been got, there is a contradiction. In the actual, there is a fringe shift was 0, and mathematically this should be equals to 0.4. So that was ruled out. So this is known as null result of Michelson-Morley experiment. Okay, so from the result of this experiment, which was negative as the Michelson-Morley has been supposed to be, the spatial theory of relativity has been come out. And what are the postulates of spatial relativity? We will discuss them in the next video. This is a building block of the spatial theory of relativity physics, because if something was in this way, this ether had been proved at that particular time, then the physics what we have studying up till now, that may be different. Okay, so I think this is a good place to stop this video. I hope you will good look and about the Michelson-Morley experiment. Okay, so in the next video we will take a look on the general postulates of spatial theory of relativity and how these Gaussian transformation varied with the with such kind of medium when the speed of light move in the absolute space. Okay, so okay, thanks for watching this video. Let's meet in the next video.